So this next problem has a slightly different feel to it. It's not so much an application as it is a very mathy, thought-provoking problem. So once again, it's got a pretty short statement. So remember, the first couple of steps in our solving of optimization problems is really read the problem, right? And then after that, try to draw pictures and label quantities, right? So that's kind of what I've done down here. Okay, but if we read the problem, it says find the point on the curve y equals square root of x that is closest to the point 3 comma 0. Okay, so find the point on the curve y comma root x, right? So what did I do? So I took this function, right? This is just the square root of x, and I drew it here, right? So here it is. So the square root of x is the function that kind of looks like a parabola that was facing up, except it fell over, right? So it really looks like this, right? And you can see that shape here, okay? And I was very careful when I drew it, so I tried to make my x-axis be spaced out as evenly as possible and made the y-axis the same, and then I plotted a couple of points on here, right? So if I plug in x equals 4 into here, take its square root, you should get 2, right? So that's where I put that point. If you take the point 9, take its square root, it should give you 3, right? So that's why give me 3, okay? And then, of course, square root of 1 should just be 1, right? So that's how I got these 3 points. So then I just drew this curve connecting them, right? Knowing that it should look kind of like one half of a parabola, but facing down, right? So it just kind of leaned over, okay? So this problem is asking us, what is the point on this graph, right? So on the graph of y equals root x that is closest to the point 3 comma 0. Okay, so the point 3 comma 0 is right here, right? So over 3 up 0. So what it's asking is which point on here is going to make it so that the distance from that point to this point 3 comma 0 is the smallest, right? So is this the point closest to this main point here, right? Or maybe it's something here, right? Maybe that's closer. Or maybe something right here, maybe that's closer, right? Who knows? Maybe something over here, but probably not, because we can kind of see that that's very far away, right? These 3 points are much closer than this point over here. Okay? So really, this is what it's asking, right? It's asking what point on the graph of this function is the one that's closest to this point at 3 comma 0, right? So which one is the closest one? Okay. So one of the things that we're going to need, so in terms of labeling relevant quantities, is we need the formula for the distance between 2 points. Okay? So this is something that you would look up, or if it was on an exam or something, I would give this to you, right? Or I would give you it as a hint, but it's definitely something you can look up. But this is the formula for the distance, right? The distance between 2 points, right? So x1, y1, x2, y2, their distance between them is given by this formula right here. Okay, so step 3 in our procedure of solving these optimization problems is finding an equation for the thing that you want to minimize. Okay, and that's exactly what this is going to be, right? We want something that's a point on this curve that is closest to this point 3 comma 0. So we want to minimize this distance, right? So we want to minimize this. Okay. So one thing we can definitely do is we can go ahead and plug in some of the things that we know already. So for example, one of these points is going to be this point 3 comma 0. Okay, so we can do that. So we can write down the distance from, so let's write this. So maybe x2, y2, that'll be 3 comma 0. It really doesn't matter, but I'm just going to write that. And then x1, y1. So x1, y1, remember that has to be a point on this curve, right? Meaning it has to satisfy this relationship. Okay, so whatever that x is, so we'll have some x value. The y value has to satisfy this equation, right? It has to satisfy this. Meaning that if I plug in an x, the y value better be given by this. Okay, so I can write down that the y value should be square root of x. Okay, so that should be my y. So then if I plug plug that into this formula here, I end up with square root, okay, x1 minus x2, so that means you're subtracting the x values here. So I'm going to write down x minus 3 squared, okay? And then the next term is y plus y1 minus y2, right? So plus y1 minus y2. Well, this is the first y value, this is the next y value. So I'm going to write down square root of x minus 0 squared. Okay, so I have this. Now let's simplify just a tiny bit. So this is the same as square root of x minus 3 squared. And then here you notice this minus 0 doesn't do anything, it just goes away. And then I end up with square root of x squared. Okay, so when you do the square of the square root of x, you end up with just x again, right? So really this is just plus x. Okay. So now one thing I'm going to do is I'm going to go ahead and multiply out what's on the inside of this square root, right? So I'm going to go ahead and multiply this out. Okay, so this is equal to the square root of, okay, so I'm going to get x squared minus 6x plus 9. So that's what I get when I square that term, and then plus that x on the end. Right, and then simplifying this a bit more, I end up with the square root of x squared plus, oh, not plus. So minus 6x plus x gives me minus 5x. And then I have my plus 9. Okay? So this is the equation, this distance, right? So maybe I'll just write d for distance. So this distance is what we want to minimize, right? So we want to minimize this. Because what we're looking for is the point on the graph of this function that is closest to this point, right? And this distance is telling me the distance away from these points to this point, right? So this distance is giving me these little values, right? So how long these little lines are. So I want to minimize this, right? I want to see which point is going to give me the smallest little line, right? And whatever that point is, so whatever that x value is, that's going to tell me where on my curve I have the smallest distance away from this point 3, 0. Okay, so we want to minimize this d. So now there is a trick involved with this type of problem, and the trick is to not necessarily focus on minimizing this function, this whole d function, but actually focus on minimizing what's on the inside of that square root. Right? So if we make the inside of the square root as small as possible, that's the same as making the whole thing with the square root as small as possible. Okay? So what we're actually going to focus on is minimizing this inside part, right? So actually, minimize, so we're going to minimize the function f of x equals x squared minus 5x plus 9. Okay? Because if we minimize this inside part, it's really the same as minimizing the whole square root. Okay? So we're going to focus on finding the minimum of this function. Okay? So now let's go ahead and do that. So, okay, so I'm going to write that down over here, that function down. So I've got the function f of x equals, so we have x squared minus 5x plus 9. Okay? We want to find its minimums, which means we want to find its critical points, right? So let's take the derivative. Okay, so find f prime. We're going to take its derivative, set it equal to 0, and then we can find the mins. So taking the derivative here, derivative of x squared gives me 2x. The derivative of minus 5x gives me minus 5. Okay? And the derivative of the plus 9, well, that's just a constant, so it's going to be 0. Okay? Now we're going to take this, set it to 0. So set equal to 0. Okay, so then I have 2x minus 5 equals 0. Solve this for x, you should get x equals 5 over 2. Okay? And this is giving me a minimum for this function f. Okay, so you might ask yourself, how do we know it's a minimum? Well, you can try out the first derivative test or the second derivative test, meaning you can try to write down maybe a number line, right? So you could write down a number line. You could put the point 5 over 2 on here. You can plug numbers into the derivative, right? So maybe pick a test point over here like 0, pick a test point over here like 3, right? And you can see whether the derivative is positive or negative, right, by plugging these numbers into here, right, into the derivative. So you can see if you plug in 0, you're going to get minus 5, so really should be negative here. And if you plug in 3, you should get, so let's see, 3 times 2 is 6, 6 minus 5 is 1, right? So that's a positive number, so plus. So you can see the function is going down and then up. Okay, so this should really be a minimum, right? And if you think about it, this is a parabola, right? And it's a parabola facing up because the coefficient down front here is positive, right? So this function really looks like a parabola. So I'm just going to draw a generic parabola here. I have no idea where it actually is in space, but it's a parabola facing up, right? Meaning that you just really are looking for its vertex. Okay? So this is something you might have seen in pre-calculus, right? So if you look for the vertex of this parabola, that's really where the minimum is happening, and that's where this point is at, right? At 5 over 2. Okay, so this point is giving me the minimum for this function f. Okay, so x equals 5 over 2 gives the smallest possible value for the function x squared minus 5x plus 9, and hence the smallest, so the smallest value for d, which was the square root of that number, x squared minus 5x plus 9. Okay, so the smallest distance. Okay, so if we think about it, this x equals 5 over 2 is our answer, right? So that's telling us that if we look back at our graph over here, when we look at x equals 5 over 2, so maybe do that in green here. So x equals 5 over 2. That's a little bit bigger than, so that's actually 2.5, right? So that's right here. Okay, so that's 5 over 2. And so if we trace that up to here, so that's maybe a point like right here. So that's a point right here, right? And if we look at the distance from that point to this purple point, that is the smallest distance, right? So this is the closest to the point 3, 0. Okay, and we've found its x value, right? And to find the y value, you just plug it into the function y equals square root of x, right? So we can write down, thus 5 over 2, square root of 5 over 2 is the closest point on the function y equals square root of x to the point 3, 0. Okay, so this last sentence here is really the solution to our problem here, right? So we found the point that is closest to 3, 0 and lies on this graph.